Good afternoon, ladies and gentlemen. Today I'm going to talk about something about machine learning. My talk is divided into two parts. In the first part, I will give a short review or kind of introduction on the machine learning, and the second part will be on my main method. Briefly, machine learning is a branch of artificial intelligence. It is also the modern tool that realizes the artificial intelligence. And this is a quite widely quoted definition by Tom Zhirong. You can see that in this definition, there are three key elements in machine learning. The first is E, that is the data. Learning from data is the major difference between the machine learning and those traditional AI approaches. For example, those logic-based or knowledge-based systems. And the second is the task T. And the more importantly, the performance of this task must be quantified. And this is the key difference from those methods which just find some interesting things. For example, data mining. And this optimizing this performance measure is also a common way to realize the machine learning. There are three major types of the machine learning problems. The first is called supervised learning. The computer is given a set of input xi's, and there's corresponding labels or supervised information yi's. This supervised information can be given by human or given from the history. And the task is try to learn a mapping function f from x to y. Then later we can use this mapping function to predict the y on unseen x. The second type is called unsupervised learning, where the computer only given these xi's. There's no yi's here. Then the task is to try to find some structure in the data. And the third type is called the reinforcement learning. A computer program or an agent, sometimes called an agent, it interacts with the dynamic environment to achieve certain goal. And then this agent can receive some feedback, for example, awards or punishment during its navigation in the problem space. I'll give you some examples of these things. The first one is the classification. This is an example of the supervised learning. Here, each xi is an image. Then the yi is the digit in that image. The task is to recognize the digits in the images. Then we supply the many pairs of such things to a training procedure. Then we will obtain a model with some parameter theta. Later, we can use this model in a classifier to predict the digit in an unseen image. The second type, the cluster analysis or clustering, is a typical unsupervised learning. Here, each square is an xi. The task is to divide these data points, the squares, into several parts. Then if the partition is based on some density, then the result can be like this. So this is called clustering. The third one, nowadays the computer can play the video games. And this is an example of reinforcement learning. For example, this game is Super Mario. Yesterday, it's very funny. I see the many Marios and Luigi in the canvas. But I didn't see any mushrooms. Yeah, but back to this question. Now the computer dynamically receives the screen in pixels. And then it needs to decide whether to run or to jump. And of course, the final goal is to pass all the episodes. Then during this procedure, you can receive some feedbacks. For example, some awards. For example, how much the Mario advances and how many coins it collects. And of course, you can receive some punishment. For example, losing lives, or the Super Mario downgrade to Mario, these kind of things. So I get this idea. Now, if you look at the next big things, in the past decade, if you look back to the past 10 years, the most successful seems to be supervised learning. But actually, these systems are quite easy to fool. And we have the tech know-how if we want to collaborate with the industry, but we are in the university, we must look forward to the next 5 years or next 10 years. Then the next big things must be in this unsupervised learning and the reinforcement learning. And my research work is mainly focused on unsupervised learning. Next, I will start my main method. People have developed many algorithms or models, from simple to complex, from unsupervised to supervised, from classical to modern. There are many others not listed here, but the important fact is the performance of machine learning heavily depends on the data representation. If you have good features, everything becomes easy. If you have bad features, everything becomes quite difficult. And because most machine learning algorithms, they take the vectors as input. So finding a good vector encoding of your data is a fundamental starting point. For example, let's consider this sentence. I love Bergen. After tokenizing, these words will become a string of IDs. But IDs, they are meaningless. They are not informative. They cannot give you any meanings of these words. Then we want to find a vector representation of the words. Then in the vector space, we hope the distance or the similarities will become more meaningful. Then we know the information is in the order of words. So a good vector encoding should respect this order. If we manage to do so, then we can use this sequence of vectors as input for the many natural language learning algorithm, for example, LSTM or other recurrent neural networks. And similarly, in biology, a DNA sequence is originally given by ACGT, this kind of nuclear basis. Then we can similarly encode the DNA substrings into vectors. The vector encoding is needed even if your data is already in the vector format. This is because quite often your data is only in raw features. For example, images in pixels, speeches in waves, and the text documents in the word counts, and etc. And these raw features are quite weak. Here the weakness means if you use some simple metric, for example, Euclidean distance or Hamming distance, this distance only works in a small neighborhood. If you look at a wider neighborhood, this metric will quickly become worse. This phenomenon in mathematics is called manifold. That is, the data distributed in a curved space. Then the research question here is that, given a big collection of such data, can we learn a good vector representation with respect to this manifold? Our method is called Neighbor Embedding. It is a class of the unsupervised learning methods. These methods try to find a vector representation of the data according to the neighborhood in the original space. Then the key point here is big. Our method is particularly suitable for big data, and we are able to do it big. This problem is clearly defined. We are given a set of data items, xi from 1 to n. Then if their pairwise similarity is encoded in this non-negative square matrix PID, then we want to map each xi to yi. Then if the pairwise similarity between yi and yj is in Q, then the learning goal is very simple. It's just to make the Q to approximate P. And then the approximation can be quantified by a certain kind of divergence. If we stack these y vectors into a matrix, then this learning can be formulated as an optimization problem. Minimize the divergence over y. it is usually non-convex and smooth optimization problem. Here is one example called the student T-distributed stochastic neighbor embedding. It is widely used in machine learning for data visualization. The input is some high-dimensional data, and we want to map each xi to a low-dimensional vector yi. Then in the high-dimensional space, we calculate the Gaussian similarity, and then we normalize similarities to be probabilities. And in the low-dimensional space, we usually don't use the Gaussian. We use the student T distribution. This is known as the heavy tail kernel. And then this kernel can compensate the volume difference in the high-dimensional space and in the low-dimensional space. And similarly, we normalize the similarity to be probabilities. Then a standard choice of the divergence is Kullback-Leibler divergence between these two probability matrices. Then we minimize this Kullback-Leibler divergence over Y. This will give us the embedding vectors. And the Kullback-Leibler divergence is not only choice. There can be many other divergences. Many of them are unified in this two-parameter family called alpha-beta divergence. You don't need to remember this equation, but I can tell you some special cases that if alpha-beta equal to 1, this is standard, the square Euclidean distance. If they're both half, this is called Hellinger distance. If alpha is 1 and beta approach to 0, this is a DI divergence. We will see this divergence again later. When alpha approach to 1 and beta approach to -1, this is called interpolacidal divergence. It's very useful for speech or music data. And when alpha is 2 and beta is -1, this Pearson chi-square divergence. But there's one challenge or drawback here. This alpha-beta divergence is not the scale invariant. That means if you multiply the p by a constant, let's say 2, then it give you a different embedding. This is not desired. We have proposed to solve this by a new divergence called the Renyi gamma divergence. It also has a Crookes term, a p term, and a q term, but now the summation is all within the logarithm. We have shown that this is also a valid divergence, and this is non-negative, and it is 0 if and only if p is proportional to q. And now this divergence is scale invariant. That means if you scale the p or scale the q, it remains the same. It has two notable special cases. One is when rho is 1 and gamma approach 0. This is standard Kullback-Leibler divergence. And if both rho and gamma are 1, this is the negative logarithm of cosine distance. The thing here is we want to enjoy the benefits in both sides. The Renyi gamma divergence is good for an objective function, but it's hard to optimize because the summation is within the logarithm. But on the other hand, the alpha-beta divergence is not scale invariant, but it's easy to optimize. But we have this finding. We minimize Renyi gamma divergence is equivalent to minimize alpha-beta divergence by using an extra variable. We'll make use of this later. Okay, up to now, some of you may ask, okay, this looks like the multi-dimensional scale, MDS, if you know this. It's a classical method for reducing the dimensionality. But I can tell you Neighbor embedding works much better. Here I give you one example. It is on the typical machine learning data set called MNIST. This MNIST contains the 70,000 grayscale handwritten image images. Then each image is 28 times 28 the resolution. So here are some samples. Then in total, each sample has the 784 dimensions. Now the task is to reduce this high dimension to be 2D or 3D to visualize the data. Here is the MDS result. But please notice the most recurrent MDS software, it cannot handle so many data points. Here is the result for only a subset, 6,000 points. Each dot here correspond to an image. And the colors here shows the digit classes. So you can see the MDS result, the classes heavily mixed. And also remember, these colors are actually supervised information. So for the exploratory data analysis, you don't have such a supervised information. Then you remove these colors, then you just see a ball without any useful pattern. In comparison, I show you this TSNE result in detail. First, we have the data. We calculate the 10 nearest neighbor. Then we get the 10 nearest neighbor graph, A, and then we symmetrize it to be similarities. Then we normalize these similarities to be probabilities. Then we supply this P to TSNE and minimize the TSNE cost. But remember, we should use our algorithm. If we use other algorithms, you may not repeat the result here. Then finally, you get the wide vectors. So you can see our algorithm clearly shows the 10 columns. So it corresponds to the 10-digit classes. It works much better than the MDS. Here's another example showing our collaboration. We have some collaborators in UK, the Sanger Institute, and these biologic experts, they have a wonderful research on the bacterial infection. But at the beginning, they are unsure whether the infection types correlate with geographical locations. Then they gave the data to us, and we run our TSNE algorithm, and we give this kind of visualization to them. And this gives them this very straightforward understanding, and then this confirms their hypothesis. So once they confirm this, our biological experts accomplished the research, and then the results is recently published in a high-level journal. There are many other interesting visualizations in the Neighbor Embedding the software website. So if you are interested, you can go there to have a look. Now next we talk about optimization. As you see, the Neighbor Embedding actually is very simple. Just a Q approximates P. Once you select a suitable divergence and suitable the normalization scheme and a suitable curve. That's it. But optimization is not tricky, because you need to calculate all the pairwise relationships. Then for this, the computational cost is called n squared for exact methods. For n is n equals to 70,000. Then you have this amount of pairs. Then if you use double precision, then you need this amount of memory to store the Q matrix. That's a lot. That's already costing out of memory for such a PC. Of course, you can do the online computation, but it's horribly slow. For exact methods, it requires about 47 hours to finish for the MNIST data. Then this is infeasible. Then we propose to use tree-based approximation to speed up the procedure. And this idea came from physics for the n-body simulations. We show that it also works for neighbor embedding. The approximation quality is pretty good, and the speed is significantly improved. This Barnes hard tree, the construction is very simple. You have a bunch of the data points. You first calculate the bounding box. Then if there's more than one data point in the box, then you subdivide into 4 smaller boxes. Then you repeat this division until each box contains only one data point. Then you get this kind of hierarchy. Once you get this hierarchy, we can accelerate things like this. Originally, you need to, for each data point, you need to calculate its relationship to all the other points. But now we only calculate the relationship to the neighboring points. For some distant points, we can use the centroid of their parent or their ancestors. So this effectively reduces the cost from O(n) squared, O(n) log n. So that's why for MNIST, then we reduce the memory to 15 megabytes in 15 minutes. That's a great thing. Recently, we further improved optimization. All the previous methods, they use batch optimization or centralized design. And this easily gets stuck in some local poor stationary points. And they don't make use of the parallel computing devices. Here we propose to solve this by this hot-wide asynchronous stochastic gradient descent. The idea is very simple. We randomly pick ij, and then calculate a partial gradient, and then update the corresponding yi and yj. But to do so, we need to reformulate the Kuiper-Neighbor divergence a bit, because in the KL divergence, the summation is within the operator. Then by using our optimization equivalence, we can rewrite this into an I divergence with an extra variable. Then this I divergence is just a summation of ij terms. Then we can use this ij chip. Then the algorithm is easy to program because there are no locks. There's no communication cost between the parallel workers. So it's very easy to code in both in CPU and in GPUs.
What is the role of the S parameter S?
Scale. Actually, the scale. That means you maximize, you approximate Q to P up to some scale, the best scale. The role of S is scale. Yeah. Then for endless data, with a GPU, we can reduce the computation time to half a minute. Then for much bigger data set, for 11 million data points, we can finish in a few hours. Another advantage of using the stochastic optimization is we can go beyond visualization. As you know, for the tree-based things, the tree will exponentially grow when you have higher dimensions. But the stochastic optimization, we can relieve these at least. And then here we apply the neighbor embedding to a text corpus. Here we remove all the punctuations. Then we have a long sequence of words. Then we use some windowing for each word. Use some windowing to get the neighborhood. Then we apply the neighbor embedding to this kind of data to find the embedding of English words. Then the resulting embedding space is 200 dimensions. Then the result, in the 200 dimensional space, we calculate the 8 nearest neighbors for some queries, 10 queries here. This query words include some common objects, some places, a very local word, and some mathematician name. So you look at these 8 nearest neighbors. They do belong to the same concept. So that means our embedding the space is very meaningful. The neighbor embedding can also be used for similarity-based cluster analysis. This originated from the non-negative matrix factorization. NMF factorized a non-negative matrix into 2 other non-negative matrices. Then in neighbor embedding, we use Q to approximate P. Then the P here is symmetric. Then the Q, it is not Gaussian, it is not T anymore, it's just a linear curve. But we impose the non-negativity constraint. By combining these two things, we will produce some sparse matrix, sparse U here, and it's close to the cluster indicator matrix. In this diagram, and this is P, a black dot appears when the 2 items are similar. Otherwise, it's Y dot. And it is approximated by Q here. This is the kind of our model. And the Q can be factorized to U transpose. But this kind of the traditional, the symmetry NMF, they still have some problems. It is inconvenient. The user, you must choose the number of clusters. And it is inaccurate. Sometimes you give some wrong cluster sizes. And it's not scalable. It only works for some small areas. We propose to solve this by a new constraint. It's called doubly stochastic constraint. That means we require the Q to be row sum to 1 and column sum to 1. Of course, optimization over such a low rank matrix is not easy. But fortunately, we show that we can equivalently rewrite these things by using this kind of cube. Here, the WIK is the solved cluster assignment. This is the probability of the K cluster given the I sample. Then, by minimizing the things over W, we can directly give the clustering answer. Then later we choose this I divergence. I skip some details here, but you know that in the I divergence, underlying the noise assumption is boson. Then you know the statistics, the boson better accounts for those sparse occurrences. Then it's easier to model the local similarities. Then the optimization again. Now here we minimize this divergence over the matrix W of something. The W should be the non-negative and the non-negative and then sum to 1 here. Then this is the optimization method. Of course, you can do some gradient descent or some traditional way by some projection, but I tried. It doesn't work well.
Sorry, you take summation over I or over J in the second?
Oh, okay, sorry, there's a typo.
Over
K. Okay, it's wrong, something one. Sorry, yeah, it's a typo, yeah.
And then what happens if WIK is 0?
If it is 0, then this algorithm has some small problem because sometimes it calls some divided by 0, but usually we force it to be positive, only small, really small. Then you can treat it. Finally, you can do a small threshold to treat it as 0. There's no big problem in practice. But the good thing is, if you treat it as positive, we can use this later, this multiplicative update rules. We don't use the extra projection. This is very simple, but it's not a standard. Maybe it's quite strange to some of you. The thing is like this: you just calculate the gradient. You decompose into 2 parts, 2 non-negative parts. Then you, by these 2 quantities, you compute the 2 another quantities. Then finally, this is the multiplicative update loop. The so-called algorithm just repeat this loop many times until the W converges. So this kind of algorithm, we don't need to specify the learning rate, and we don't need the extra projection. The resulting W will automatically converge to the syntax. So it's easy to program. In MATLAB, I just do it maybe 1 screen. Okay, let's look at the results. Our method is called DCT. It shorts for a 2-step random of data cluster data. I skip the details here, but that's what it's called DCT. We compare it against many other methods, and we run it on mainly the data sets. Here, these numbers are the clustering accuracies. Larger is better. And the boldface indicates the winner for each data set. And these data sets are ordered by n, from small to large. So you see, for small data sets, every method can occasionally win. That's why you see so many clustering papers. Some people, they just run a bunch of papers and then do some cherry picking and then publish the papers. But you look at the big data, things are different. Our method has a much better chance to win. Especially if you look at this MNIST, the clustering accuracy is 97%. It's already quite close to supervised learning. But remember, our method is clustering is completely unsupervised. And the neighbor embedding also has another advantage. It is not only for a single cluster, it can compare different clusters. And we don't need extra the evaluation criteria, for example, the gap statistics or whatever. We can just minimize the divergence. We test our method on 5 data sets. Here the blue line shows the ground truth. This red curve is our objective over different number of clusters. And the red star indicates the minimum, that is our selection. Then we can see that our selection is often or sometimes exactly coincide with the ground truth. That means our method is quite accurate for this purpose. Okay, final the research question. I have shown you we have a very flexible family of divergence. You can just pick one of them to which suits your application. But sometimes people want to do this automatically. How can we select the best divergence? Can this also be learned? Yeah, we are the first one which solve this problem. We start from this beta divergence because in statistics it relates to this the 3D distribution. But we find that it is the 3D distribution. It is not defined for all beta, and it is also very, very difficult to estimate. We must use some ad hoc and slowed methods. So we propose a modified 3D distribution. It is based on the exponentiated divergence with some augmentation. We call it EDA. And this augmentation comes from the Laplace approximation. Then by using this kind of density, we showed it is a valid density. Then choosing the best beta becomes the standard maximum likelihood approach. Then it also works for all beta, all real value beta. Then for some other divergence, alpha or E gamma, for alpha divergence, we can use this kind of transform to convert it to the beta case. And then for gamma and E divergence, we can use our optimization equivalents to convert them back to the beta and alpha cases. Okay, here's a summary. Today I have talked about the method learning the data representation. And it learns the vector encoding from the massive local information. Our method is called Neighbor Embedding. It is based on very straightforward matrix approximation. And we have efficient and scalable optimization here. This method can directly be applied to data visualization and cluster analysis, and can also be used for the generative feature extraction. In the future, I've ended up with my talk by one picture. A famous machine learning expert, Yan LeCun, has compared these three types of machine learning problems to the K elements. You see, the pure reinforcement learning corresponds to the cherry. Supervised learning is the icing, and unsupervised learning is the cake itself. So you can see the importance of unsupervised learning. It gives the basic support of the cake. It gives the common sense to machine learning. So in the future, I will continue working on unsupervised learning. And that's all for my talk. Thank you.
Thank you very much. We're open for questions. Stefan.
Yes, thank you very much for the nice talk. So you showed an example with TSNE, which is very, very popular, partly because it really shows a nice structure, and some of the criticism that has been raised is that it overemphasizes structure as well as other issues such as that the distances between clusters are really meaningless. Is this something that is in general true for neighbor embedding algorithms, and what can be done about these issues?
I'm guessing you're asking some drawbacks of TSNE.
I'm asking whether these known drawbacks of TSNE are specific to the algorithm, or are these in general true for neighbor embedding approaches?
Not necessarily. For neighbor embedding, we just it depends on which the divergence, which the kernel you use. The TSNE has a tendency to split the data. Yeah, but this is needed when you see the big pictures. Clusters are the big pictures. When you reduce the dimensionality, you must lose something. You must have some distortion, but it depends on what you need. But now, if we want the big picture, clusters is quite often is the important thing. So you will split the things to get the clusters. But of course, if your thing is continuous, if you use TSNE, you have the negative effect to segment the things.
Yeah, but one of the issues with TSNE, for example, is that this splitting is not or it's only very loosely data driven. So you may have nearby clusters that are not closer than something that is far away. In fact, you can have different configurations in different runs, which can be very misleading when you try to learn something
if
from the data.
Your data is like that, then it can be misleading. Yeah, I agree. There's no problem. Yeah. And this splitting is mainly caused by the T kernel. If you choose a different kernel, the splitting can disappear.
Yes.
Thank you very much for a very nice talk. It was a very pleasure to listen. So when you read the popular literature about machine learning, like for the last 5 years, it looks like almost everything is about deep learning. But it doesn't seem to somehow interfere with your research program. So can you comment on that? So what deep learning is for you?
Yeah, deep learning, deep neural networks. What's the input for deep neural networks?
But how it's related to your research?
Vectors,
Or it's not related?
You see, the input to deep neural network, you must have vectors.
Yeah.
And also, maybe the very popular one, you see for the natural languages. This you have the recurrent networks. The first step is called the word-to-web. Word-to-web can be shown, can be proven to be a special case of neighbor embedding.
Okay.
Yeah. And also, of course, the thing here is mainly neighbor embedding is existing and kind of my established work. In the coming years, deep neural network. We will work on deep neural network. Especially now, what I show here, they are non-parametric. So I only care about the x back to y, but I don't care about the mapping function itself. So if you want the mapping function, it must be a deep neural network.
Okay.
Yeah.
Thank you.
Okay. Yes.
So you were mentioning about some tree-based optimization in one of your slides, and then you said that you get nearly lossless in something. So what do you mean by nearly lossless approximation?
That means that if you calculate the exact objective function and approximate objective function, you compare these two, you find it almost the same. Also, you compare the gradient, approximate gradient, compared to some norm. You see,
so is it heuristic or is it provable?
bias height is not provable. It is in practice. If you want provable, you use the fast multiple. But we didn't choose fast multiple because it only have fun in theory. It doesn't work for heavy tail kernels. Then the thing we need heavy tail, we need T kernel here. That's why we didn't choose fast multiple. So we sacrifice some provable things. But in practice, it works.
Yes.
I didn't fully understand what your comments about deep learning. So what you mean is that the approach you have proposed that can be used to pre-process as inputs like words, like images, and then the output of your approach can be fit into a deep neural network. Is that what you mean?
Yes, my output. Yeah. Output is a good vector encoding supplied to deep neural network.
So that can improve the performance of.
For example, in the example, for the text words, if you just apply IDs to deep neural network, it doesn't work. It's very sparse and very hugely high dimensional. It doesn't work. So the first step you must reduce to several hundred dimensional.
Okay. Mike.
Thanks.
Comment?
Yeah. Your neighbor embedding reminds me of a recent visitor we had here, Gunnar Carlson from Stanford, and he has this company that they're in the Bay Area that's for the last couple of years called topological data analysis. So they're using something like Morse theory and high-dimensional manifolds and stuff like that. It seems very closely related. Do you know their work, or can you comment on
I don't know. But the topological preservation is not new. When I went to Finland many years ago, actually I was attracted by these self-organizing maps. It is also topological preserving. But that's old-fashioned. So there's quite a lot of other methods doing the topological preservation, but so far the neighbor embedding seems promising.
Okay. Thank you. I guess there are no more questions, so let's thank the speaker once more.